instead of drawing all that stuff, we'll draw a little box called a z-hat box, a Stern-Gerlach apparatus. In comes a beam. Out would come two beams, Sz equal h bar over 2 and Sz equal minus h bar over 2. In the conventions that the plus goes up and the minus goes down, which I think is probably consistent with that drawing. And that's the Stern-Gerlach apparatus. It measures Sz and it splits the beam. Each particle goes into both beams until there's a device that measures and decides where you go. So you can do the following arrangement. So here is arrangement number 1. A Stern-Gerlach device with Z. Then you block the lower one and let the top one go, has Sz over h bar, Sz equal h bar over 2. And then you put another Stern-Gerlach machine, Z hat, that has 2 outputs. And then you ask what's going to happen. And the experiment can be done. And actually, there's nothing here coming out. And all the particles come out here with Sz equal h bar over 2. What are we going to learn from this? In our picture of quantum mechanics, we're going to think of this as there are states of the electron that have, and I will write them, with respect to Z, they have plus h bar over 2, and states that have minus h bar over 2. And what we will think is that these are really all the basis states. That any other state, even one that points along x, is a superposition of those two. This is a very incredible physical assumption. It's saying this system is a two-dimensional complex vector space. Two vectors, two basis vectors, and from those two, all linear combinations that are infinite represent all possible spin configurations. And what is this saying? Well, as we will translate it into algebra, we will say that, look, here is a state plus, and when you try to measure if it had any minus component, it had nothing. So we will state that as saying that these states are orthogonal. The minus state and the plus state have 0 overlap. They are orthogonal basis states. And for example, well, you could also do it this way. That would also be 0. And you could also say that Z plus and Z plus is 1, because every state that came in as a plus came out as a plus. They had perfect overlap. So these are two orthonormal basis vectors. That's what this seems to suggest. And it's a little strange if you think, because there's a clash between arrows and the notion of orthonormality. In three-dimensional vectors, you think of this vector being orthogonal to this. But you wouldn't think of this vector being orthogonal to that one. And here is the spin is up, and this is the spin down, and those two are orthogonal. You say, no, they're anti-parallel. They're not orthogonal. No, they are orthogonal. And that's the endlessly confusing thing about spin 1/2. So these states, their pictures of the spins are arrows. But don't think that those arrows and a dot product give you the orthogonality, because this is up and down. If you would be doing the dot product of an up and down vector, you would not get 0. But this is 0. Then you do the following experiment. Oops. So let's do the next one. And the next one is, again, the Z filter. Take this one, block it. Then you put an X filter. And what actually happens is that you would get states with Sx now h bar over 2 and Sx equal minus h bar over 2 because it's an X filter. The magnetic field is aligned in the X direction. Now all these things have Fz equal h bar over 2. And what happens in the experiment is that 50% of the particles come out here and 50 come out there. So a spin state along the x direction has some overlap with a spin state along the z direction. Normal vectors, a z vector and an x vector, are orthogonal, not here for spins. The spin pointing in the z and the spin pointing in the x are not orthogonal states. They have overlaps. So this means that, for example, the x plus state and the z plus state have an overlap. This is notations that we're going to be precise later, but the same thing with the x minus state. It has an overlap, and somehow they're about the same. Finally, the last experiment is this. Z hat, block again, x hat, but this time block 1. So here is a state with Sx equals minus h bar over 2. Here is a state with Sz equal h bar over 2. And now you put a z machine again. And what happens? Well, there's two options. People that were inventing quantum mechanics, no wonder, thought about them. Here they could say, look, I filtered this thing, and now all these electrons have Sz equal h bar over 2. And now all these electrons have Sx equal minus h bar over 2. Maybe, actually, all these electrons have both Sz equal h over 2 and that, because I filtered it twice, so it maybe satisfies both. So if all these electrons would have Sz equal h over 2 and this, then you would only get something from the top one. But no, that's not what happens. You get in both. So somehow the memory of these states coming from Sz equal h over 2 has been destroyed by the time it turned into a state with Sx equal minus h over 2. And the state cannot have simultaneously this and that as two properties, because you get 50% here and 50% there. So we'll discuss next time a little more about these relations and how can these states be related, the ones that we use as the basis vectors and all the others along x and others that we could build some other way.